This is number 10 from the test. I forgot to start recording at the beginning of what we were doing. Welcome. Here we go. Okay, so yeah, so I think I said 2i squared out loud, but I didn't write it. Plus 2i squared. And then the denominator, it's just the f and the l, right? So the first is 3 times 3, which is 9. And then I times negative I is negative I squared. And then what do we do?
Then you add all the stuff on the top that needs to be added and you change the I squared to negative.
True facts. So 3 minus 7i minus 2 over 9 plus 1, which was where you made the mistake. Each made one mistake, just a different one. Both dealing with the denominator. No, that's not true. Okay, what now?
Then you add stuff on the bottom and the top that needs to be added, so it'll be 1 minus 7i over 10.
Over 10. And this is the problem where I said I would have. No, this is not the problem. It's the quadratic formula one. So in order to be in correct complex number format, we can't leave it all shoved together. We got to split it up. So what do we got to do?
1/10 minus 7i.
1/10 minus 7i over 10. Did you remember now? Oops.
Yeah.
Okay. Are you okay doing 13?
Did you have one?
No.
Okay, 13. 13 it is.
I have a question on every single one of them except for the last one, technically.
You might want to schedule some office hours. You don't have to, it's not required, but you might want to.
So most of the time I just miss like one negative sign and that is what kills me.
Yep, that's what happens. Little mistakes. It's no big deal. Doesn't even matter. Unless you're paying taxes. Okay.
13. I felt good about 13.
Borrow your 13. Let's see. So number 13.
13 doesn't factor, does it?
It does not factor. Even though it looked like it was, were you the one that looked like it factored, but then you forgot to check the end sign? Is that what?
I thought about the end sign. I put a lot of thought into the end sign.
Uh-oh.
I just did it wrong still.
Gotcha. If that 6 was a negative, this problem would have been a lot easier. But it was not a negative. It was a positive. Okay, so this one, I already said, doesn't factor. Just for point of contention, if you try to factor it, which is not a bad thing to try to start, we can go like 3x and x, and then you might do 6 and 1, and you would go here and go 1 and 18 and be like, oh, that seems to work. Because that gives us negative 17. However, if we do that and follow our signs, a positive times a negative at the end would give us a negative. So it does not, in fact, factor, right? So just to clarify for the room and the internet, right? So since it doesn't factor, we could go through all the other permutations and thrice prove that it's not factorable, but we'll take our word for it and we'll prove it by doing a different method. So we can either use the quadratic formula or we can do completing the square. If we do completing the square on this problem, we're going to end up having to deal with fractions. So we may want to use the quadratic formula. What is your vote?
Quadratic.
I've heard one vote. Okay, quadratic formula it is. So let's quickly write the quadratic formula. What is the quadratic formula?
Negative b plus or minus the square root of b squared minus 4ac over 2a.
Okay. So start plugging stuff in. Oi. Yeah, you'll need to tell Tinsley that we've actually been recording class and actually been releasing it this year. So she missed her chance to be a star. Well, they were both excited about the idea, but yeah, you could tell Mia too. And then
I've seen her picture.
I haven't seen her in person, only on Be Real.
I use it on Be Real.
Yep. Okay, so negative 17 is positive 17. Plus or minus the square root of 17 squared, which is 289, right? Am I remembering right from my key?
Yeah.
And then minus 72 all over 6. What's 289 minus 72?
217.
217, which is a prime number.
Oh, that's why I was having so much trouble.
Oh, yeah. It's got to be simplifiable. Has to be.
So you're gonna have to go somewhere from there?
That's as simple as it's got to be. Done and dusted. If you could reduce this radical, then we'd have to do that, but it's not reducible.
Okay. And then I guess 14 is outside issues on that.
Okay.
Which one, 14?
Oh, yeah. Same thing, different numbers. This is also not factorable. It doesn't even have a real answer.
Oh.
So number 14, we'll call it quits on the test after this one. If you have more questions, you can ask through Google, whatever, I guess. Or you can stick around for a minute or something, or whatever else. Don't know. All of this stuff, the reason why we do this much of the review chapter is all of this stuff is applicable, like it's going to get used more. So that's that. If you are confused, I would recommend getting help from me or Khan Academy or your dad or something else. Like if there's something in this test that you can't do, I would recommend spending some time rectifying that problem. All right, so quadratic formula, here we come. So x equals negative b plus or minus square root of b squared minus 4ac all over 2a. So negative 13, negative 13, negative 2, and negative 23, and negative 2. So negative 13 squared is some number that I don't remember. 169, is that what you said?
Yeah.
Okay, that sounds accurate. 13 plus or minus 169 minus, and it's going to be minus because we got a negative times a negative times a negative.
184.
184. And over negative 2.
Negative 4.
Thank you. 13 plus or minus the square root of negative, whatever it is, 15, right? 15 is not prime, but there's no perfect squares in it. But we do got to deal with that and turn him into an I. Minus I times the square root of 15 all over negative 4. This problem is the one that I said during the test that I will count it right even if you don't do technically correct, because a lot of textbooks will leave this just like that and be done. If we want to technically get it even more right, we'd split it into the real part and the imaginary part. You can use just the plus or minus symbol in the middle.
So it would be 13 over negative 4 plus or minus.
I times square root 15 over actually it doesn't even matter whether it's negative 4. You could put negative 4 or positive 4 because of the plus or minus. Yeah, but this is really the most common with things from this with quadratic formula stuff. This is the most common way you're going to see these anywhere, even in college. They for whatever reason typically leave those just like that, smooshed together. Okay, let's look at functions. Isn't that what we did today, right? 1-1. On to chapter 1, which is still kind of review with a twist. With new notation that you probably have never seen before, which has enough in it that I think we're going to put it on the television screen instead of me reading it, because the symbols are squiggly enough that if you don't have it in your head solidly, you might think that you got the right answer, but then it's not. So let's get a picture and pop it up there. What numbers did we do on this lesson?
2 through 28.
See if Rochelle stole my thing again. I bet she did. Yep, she did. I shall return.
You don't know that. How
Keep
can
stealing
you know
my
that?
remote.
Oh yeah.
You got two of them again.
No, this one is for this, and that one is for that. I had 3 the
They
other day.
probably both work
Not
for
well.
both.
I tried.
Oh,
and
okay.
That's why I didn't steal yours.
I see.
Have fun.
Protons.
Yeah, I told you it was biology, but it's chemistry.
Yeah, that's the fun part of biology. All right.
The wrong way. I was trying to open it this way.
So now that you've learned, well, I don't know. These videos, these early videos are old enough that I may be lying and I may have not said something in a video that I'm going to tell you that I did say, and so you'll just have to be like, you didn't say that. And then we'll all deal. Hello, machine. Oh, it's because I unplugged it. Like I don't have any power. I'm still asleep. Wake me up before you go. All right. Numbers 2 through 10, here we come.
And it's not gonna matter which letter you took, right?
No. Well, if it gives you a letter, then it does matter. Like on 2, it's X. What are you talking about? Like for 12. 12, yeah, 12 doesn't, yeah, you could use X or N or whatever else.
But if it gives you a number, then use that number.
Letter, but yes. No, not that button. Good gosh. Struggling today. My brain is not braining today. It's no fun. No, not that. Nope, this might be Rochelle's. Why is that one not showing up? Life is no good today.
There it goes.
Oh, there it is. Good job. Go team. OMG. All right, here we go. All that to say, number 2. So I told y'all this in Algebra 2 last year. We were in my Algebra 2 class. In Algebra 2, we write our set, like domain and range and things like that. We wrote it in interval notation. And odds are, if you do math in college, that's how they're going to want you to do it, with interval notation, with the parentheses, the brackets, and whatever else. Every math class other than the one theoretical math class I took, every other class used interval notation. We're going to learn set builder notation, and which is how we're going to do it in this class. So when we write domain and range and all that kind of stuff, this is the style we're going to do, right? So 2 is all. So you got to learn the supersets and add in the bits that are obligatory. X such that whatever else. Is this a thing that I covered in the video, or did I go off book and say something else? Okay, good. I'm glad.
I'm confused as to why some of them up there are R and I wrote Z. Are we not supposed to write them as like the least? R is the said to write it as the one that's still in companies, that's the smallest.
I may have said that in the video. I'd have to go back and watch. I don't know what I said exactly, but it's the set that holds all of the things. So like on number 2, for example, if x is greater than negative 13, then it's everything. But on 4, then it's just the integers. It's actually not. Yeah, it's just because it's just the. So it's actually. I don't know what I said in the video. Oh, I'd have to go back and watch. I may have worded something that came out confusing. I don't know. I'd have to go back and look. After a video or two, all the videos will be new. So you'll have updated brain Sean in the new videos. So
And how are we supposed to do 4? Because I ended up
Magic.
writing it just as the parenthesis and bracket.
oh, just the interval notation. Okay. So for set builder notation, for number 4, it lists -4, -3, -2, -1, and then has the dot. So it's forever, right? So you don't have to use x. So the problem, for the sake of folks playing along at home or whatever else, that's what it lists. So for set builder notation, it's in curly brackets because that's how sets live. And then we pick a variable. It doesn't matter what the variable is in this problem because it's abstract, so we typically use x or n. So x such that, and then it's -4 or bigger, including -4, right? So x is greater than or equal to -4. And then x is a member of, or an element of, the integers.
Okay, then why can't you write it as the bracket parenthesis thing?
Because that's not how we're writing it. And it's also, and for more, why does it not have the interval notation on this problem in the answer? Because you can't represent anything other than real numbers with interval notation. Because you have to be able to say that it's only the integers. Yeah, that's a great question. Okay.
What number was that? Was that number 4?
That was number 4. Yes, sir. All right.
The only one I thought I got right, I got wrong.
Well, that's all right.
Because it-
There's, no, I don't want to copy any text. Thank you. 8 and 10. And then back to camera. Wait, what is happening? Oh, that's what's happening. Heaven help us.
I didn't finish looking at them.
Oh, you didn't? Well, I'll go back for you. It'll let me. Oh yeah, 'cause 10 is complicated.
How did I do that so wrong?
And besides the integer, it's real number thing, I'm getting it pretty right.
Wait, okay. What do you...
Let me see what you wrote, and let's see if I can figure out what you're
I
doing.
did a completely different thing.
Oh, did you watch a different video?
No, I did the other thing. I don't know what to call it. I don't know what that-
Interval notation. So the only thing wrong with your interval notation is it's backwards,
Yeah,
right?
that's how I was-
So we go small to large, right? So the littlest number would be -infinity, all the way up to whatever it is, 61. And then I put that on the board for the camera, but the camera wasn't even pointed at it. That's funny. Okay, great. Anyway, yeah, so you just wrote it backwards. So small to big, -infinity up to the littlest number, and then up to, yeah, so always small to large in interval notation. And set builder notation is just all the extra bits.
And why did I skip the set builder notation?
That I don't know. You probably didn't read the instructions and just kind of YOLO'd your way through it. It would be my guess, but I don't know. All right, numbers 12 and 14. Here we go.
I read the instructions, I just forgot to.
Well, that may be true too. Just for God is definitely a doable thing. 12 and 14, there it is.
What the crap?
Chose the right one.
12's got to be set builder notation because it's got an n in it. It's a whole expression, I guess is more what I mean.
Why is there two variables? What did I miss?
Two variables on page one.
There's n and x on 12.
We probably won't want to look at 12. I imagine we'll have a question on 12. And then 14 is fairly straightforward. What did we go through on this lesson? 28. Okay. Number 16. Let me carry my book and I'll flip my camera while I give you some other answers. Number 16 is not a function. Number 18 is not a function. Excuse me. Number 20 is a function. Number 22 is not a function. Number 24 is not a function. Number 26 is not a function, and 28 is, in fact, a function.
Doesn't that have to do with how many bodies are in the problem?
How many y's are in the problem?
Y's versus x's.
Let me
24.
let me click this button and then so that I can give you my full attention and say what. Now, like on number 24. No, it's not. Okay, so it is kind of how many y's. So it's because y is squared. So remember from when we did conics briefly at the end of last year, that would be a parabola turned sideways, right?
Yeah, there's multiple y's, that's what I'm saying. So
Yeah.
there's more y's than
Yes.
x's.
Well, so on the graph ones this year, what the easiest way, if you're like not sure, is to punch it into your graphing calculator, and then remember you do the vertical line test and see, and that would be, so if it touches twice, so it's x repeating, but yeah.
So typically that's how you do it, just put it in the graph.
Yeah, I mean, the more familiar you are with the thing, with these functions, the less you actually need the graphing calculator.
I got them all right. I was just
Trying to remember why you got them right.
What happened?
Yeah. Let's see, where's your y equals? Right there. There's nothing, Garrett. It's not graphing anything. You don't have a function in there.
Yeah, but I was like.
What are you trying? I don't know what happened because I don't know what you're trying to do.
Why is like the lines ending? Is that a problem or?
Why is the
No,
lines
remember
ending?
No, remember you zoomed somewhere, I think?
Yeah, your window settings are probably not default. Probably.
How do you do that?
Thank you. Okay. What questions do we have on page 9 stuff?
Window, and then 2, and then you'll scroll down to zoom standard. Resets it.
No questions?
We have questions, I was trying to figure out what questions.
No.
Let's do 12.
Yeah, 12 is once you kind of understand the basics of set builder notation, 12 is the only one that I would argue is all that hard once you understand the basics, right? Because if you don't understand, everything's hard, right? But once you get it, 12 might be a bit confusing. So let's do it. So we're supposed to, in set builder and interval notation, if possible, represent a set with all multiples of 8. What did they say? I was reading 13 the whole time on 12, and I was like, the key is like stupid. What happened? So number 12, all multiples of 8. Okay. So for things like this is why set builder notation exists. Because if you wanted to write this set, you would have to just start listing 8, 16, etc., right? 8, 16, 24, all the things, right? And that's, you just got to write and write and write. So they made a shortcut way to write all multiples of 8 in math. Okay, so for set builder note, and we cannot do this one in interval notation, because the only thing, and I said this earlier, but I'll say it again, the only thing that you can represent with interval notation is real numbers. So if it's all real numbers, because there's not enough information in interval notation to write this one. Okay, so we've got to build our set. Here we go. Start with our set. We use the generic x such that. Now we got to figure out how to write a math expression that says all multiples of 8. So what does multiples mean?
Everything that you multiply by.
Yeah. So x equals 8 times n. Right?
And you have to do a different variable there?
Yes. And actually there are ways to get even more specific, like what n is, but this is enough for what we're doing. We have to say that n is in fact a member of the integers.
That's not how you write this. If I don't do the extra fancy z, will you take off points for that?
Possibly. Depends on how grumpy I'm feeling.
What's the extra fancy thing?
The fancy z in this case is ugly, so there it is.
Yeah.
Because and so if you think, I may be like saying words to people that are like, okay, I get it. You don't have to give all the extra words, but all the integers, right, are all our counting numbers. So if we want to find out what something is a member of this set, we just start throwing integers in there. So 8 times 1 is 8. 8 times 2 is 16. 8 times -1 is negative 8. And so you could build this whole set from this definition, which is why it's called set builder notation. So that's what it's trying to do. And if we were to do something like this in the computer, then it would do all that for us, and it'd make this big old math thing, right? Any other questions on this lesson? It's not too tricky of a lesson. Next, on Tuesday, the first video will be out today. The second video will be out hopefully today, but soon, regardless.
How do you know when to do set builder and when to do the other one? Like, 'cause some
If it doesn't say in a problem, like in the future, past this lesson, if it doesn't say, put it in set builder notation is the standard for this class. Now, like are you talking about like some of the ones that? Okay, so that it also says if possible, right? And so it's not possible to. So if it's not all real numbers, is the set that it's a part of, then you can't do interval notation. So like the ones that are integers only, so like number 4 or this number 12, if it's integers only or whole numbers only or whatever, if it's only a part of those, then you can't do interval notation. Es imposible. All right, what time is it?
We have 30 minutes left.
We may in case it takes longer to get the second video out than I want, we may start kind of looking at some stuff from 1.3. So we're going to call this 1.3 supplemental note. So if you want to start some of the homework earlier, and I don't have a notes video for you yet, then you will have something to go on that's more than just the book. The book is good. The pre-cal book the lessons are actually pretty well done. They're pretty well written. So using the book even if you have a notes video, using it as an extra resource is encouraged. There's also 5,000 other places on the internet to figure out how to do stuff too. I'm not saying to just, like drop the class and go do whatever, but okay. So 1.3 is on continuity in behavior and limits. So lesson 3 of this pre-cal class is kind of the first truly pre-cal thing that we've talked about. It is where the limits is usually kind of the first thing you learn in your calculus class. And so this is really the true first bit. So the first thing that we're going to learn is about a continuous versus a discontinuous function. I was right. And just like it's been true when I've done this type of thing in the past, if you get to the video and you already have basically the same notes on the thing, you can scrub forward and that can count as your notes if you want. You could also rewatch it to have it sink better in your brain. So I leave that part up to y'all. Y'all know yourselves and what is useful to you and what is not. At least I hope you do. So a continuous function is probably one that continues, right? That doesn't quit, that doesn't stop. Now, as we'll get more specific in the video and stuff, but you can have a function that is continuous over part of its domain, but not continuous over another part. Okay? So a continuous function is something like this that goes on and doesn't have any holes, doesn't have any gaps. It's not a piecewise defined function that's got, oh, that was terrible, sorry, that has different parts and all kinds of things. So a discontinuous function is one that doesn't just continue smoothly, right? So there are 3 types of discontinuity. Type 1 is infinite discontinuity, which we have seen lots of. The example they give in the book, which we'll just use here for now, probably use a slightly different one in the video, is something like that. What kind of function did I draw? Do y'all remember what that kind of function's called?
X to the negative 1 power.
Yes, so that's what the definition would be. So it's a reciprocal function, right? Reciprocal of x. And that's what it looks like. So he has an infinite discontinuity. So what are the dotted lines called? What is the name for those? Asymptotes. That is true. They are called asymptotes. So if a function has an asymptote, then at that point, it has an infinite discontinuity. So infinite discontinuity goes with asymptotes. Okay. The second type of continuity is it goes with everybody's favorite piecewise defined functions, which they're getting pretty close to in Algebra 2. They're going to love it. Okay, so something like that, where it jumps from one place to another place and it's discontinuous because it's not connected, right? And then the third type of discontinuity is a...
On the jump, the ends, are they always going to be on the same y?
No, not always. Most of the time, you mean the same x, right? Yeah, no, that's good. I just want to make sure I'm answering the question correctly. So most of the time when you define a piecewise function, they will be on the same x because it changes that point, but they don't have to be. But that is going to be, by and large, the majority of the time, just because of how situations work. So the last one is the most obnoxious because when you draw a line the way you draw, it's never going to show up on a graphing calculator or a program on the computer, or well, there might be some program where they did it, because a point has no space, and so you're not going to be able to see it. But we usually represent it with an open circle somewhere because it's got a hole in it. So a function where you can't have one value, but it doesn't make it an asymptote.
Why not?
Well, when we look at when we look at some functions that have it, it'll be easier to understand. Things like there are some kinds of reciprocal functions, not reciprocal functions, some kinds of rational functions where it makes a whole and doesn't make an asymptote. And so when we get back to rational functions, it'll be easier to explain when there's like stuff on the board with like lots of stuff. We will hit it this class, just not today. So your question will be answered. Okay, so those are 3 types of discontinuity. And we have to figure out how to test whether, actually we're going to kind of talk about some of it using some examples because we got to be able to test whether it is. How are we doing on time? 12. All right, we still got some more time to add some things. Let me make sure this isn't a student.
Telling me to get
No.
moving.
Yep, you're being too sedentary.
Too lazy.
Too lazy. Lazy. Okay. So, how can you tell a function is continuous without just graphing it on the graphing calculator? There are some tests for that. There's an app for that. I mean a test. So continuity test, trying to figure out whether oh yeah. There is a fourth. I probably won't even mention this in the video, but since we're doing this live and whatever else, there is a fourth type of discontinuity, which is uncommon, and they talk about it at the top of page 25, because sometimes you can have a point instead of being removed as a whole, it just in this one situation and at this one point in time, it's actually up here. We're usually talking about things like statistics, and we're talking about things like electron probability type stuff. We're talking about like some wonky like high-end physics stuff when weird stuff like that happens. Most everyday ordinary circumstances wouldn't be modeled that way, which is why it's kind of shoved out as another thing.
Will it be on the test?
No,
I guess we won't need to learn.
no. Like I say, it's probably not even going to be in the video. So but it is an aside that sometimes that can happen. And if you want to read about it, it's right there. All right, so continuity tests.
How many are there?
3.
There's 3 tests.
Three things that have to be true in order for a function to be continuous. And we haven't talked about what limits are yet, because we're doing it out of order what they do in the book. So you're not going to understand what these tests mean until we talk about limits. So here we go. So continuity test. A function is continuous if and only if. Oh no, just kidding. Just kidding. At x equals c, if, they didn't add only if, but whatever. If it satisfies. Look, Bree, it's one of those slides, but live. The following conditions. Do I need to pause the video?
No, you're good. I'm just kidding.
Okay. Condition 1. F of x is defined at c.
Ethan keeps stealing my whiteout. It's driving
And
me
another way of thinking about that is f of c exists. If it has a definition. If it doesn't, then there's probably a hole there. Well, actually there could be any of them. If it doesn't, something's happening. This is the bit where you don't know what this means yet until we say what a limit is. F of x approaches the same value from either side of C. Sorry, I was just looking at the notation because I wanted to see which kind they used. So the limit as x approaches c, do they give? No, they don't. Of f of x exists. Yeah. And then yeah. So let's take a timeout. And jump over to what is a limit. So I think let's use two different functions as an example. So the reciprocal parent function as one example, and the exponential growth function as a second example. Okay. So, I should make these different letters since we're talking about them both at once, and I can use words. Okay. Sorry, pen users. So, what is f of 0? Look again. Undefined. True facts. It doesn't exist there. So first qualification done. We don't even have to think about limits on this one. Right? This is not continuous at that point. What is f of 0? No. If I put it. That's weird. I bet it's a butt dial. If I put a 0 there, it's undefined, right? Right. True facts. Okay. So it doesn't exist there because it's undefined there, right? And so if we were just testing whether this function is continuous at a specific point, and it's worth noting that when we're doing these continuity tests, it's not looking at the whole function. Is this a continuous function? Is the whole thing continuous? It's looking at, is it continuous here? Because if I did a continuous function, if I did this test here, right, at this point, then, excuse me, then it is continuous, right? It's continuous here. It's continuous all the way up to 0 and all the way past 0. But at 0, it's not continuous, right? So it's not continuous there. Now let's talk, but it does, in fact, have a limit there, depending on which way we're approaching. So it's not defined there, but it has, depending on which way we go, it has a limit. So a limit is what it's approaching. And it's as we're moving in the left or right direction, what number is it getting closer to? So if I am approaching 0 from the left, then our function is getting closer and closer and closer to negative infinity, right? If I approach it from the right, then it's getting closer and closer to positive infinity. So its limit as it approaches 0 from the left is one thing, as it approaches 0 from the right is another thing on this one. Now this one, it exists everywhere on the real numbers. Its domain is all real numbers. So this one would not be true if the domain isn't there, right? So this one always exists, so that's not going to be helpful no matter where we are, the first one. So the limit as this one goes to, as the function goes to the left over the course of the whole thing is approaching 0. So the limit as x approaches negative infinity is 0. But as it approaches positive infinity, the limit would be positive infinity because it's getting bigger and bigger and bigger. That make sense? Okay, that's what a limit is. So let's go back and get our third condition if we have time. Are you dying of frostbite?
Yeah, and also just not quite comprehending.
Okay, where are you?
What makes the infinities make it a limit or not?
So it has a limit. The limit is just it is just the thing. It has a limit. It's what the limit is, and the limit is not a static. It usually has a static number, but it's not a static thing. So it's as the graph is moving in a defined direction, what is it getting closer and closer to? Right? So in this instance, if we track here, we're going closer and closer and closer. And on this one, whatever this is called, exponential function has an asymptote at 0, has a horizontal asymptote at 0. So this graph is going to get closer and closer to 0, but it's never going to get there. No matter what we put in for x, if we put in more and more negative numbers, it's just going to get smaller and smaller and smaller. It's just going to get littler and littler and littler, right? It's never going to actually make it to 0. And this one, if we put in bigger numbers, it's going to keep getting bigger and bigger and bigger and bigger and bigger, and it's never going to stop getting big. So as it's going to the right, it's approaching infinity because it's going to keep on going forever and ever. Does that make sense? Does that help or?
I understood that, but I
Oh, okay.
don't understand why that makes it a limit or not.
Why it makes it
What is a limit? I don't understand what a limit is supposed to be.
a limit is what it's approaching. That's what it's defined as. What the function is approaching as it's going in a certain direction. It's more abstract than most definitions that we've had previous to this in math.
I don't like abstract math.
Well, real math is pretty abstract. As we get to more and more real math, it gets more and more abstract. The concrete math is where where the engineers and the physicists live. Well, actually, physicists live some in abstract too.
Okay, what's the third rule?
Third rule, here we go. And then probably we leave, yeah? Third rule. Third rule, and then go away, and you can watch the rest of the video with examples and all the things later. Okay, third rule is the value that f of x approaches that f of x approaches from each side of C is f of C. Another way of writing of that would be the limit as x approaches C of f of x is f of C. Yeah, okay, I understand what's happening on the notation. I was confused for half a second. That's what happens when you just do something without stopping to think about it before you do it. So if it doesn't have, so if we want to say x approaches c from the right or from the left, we put positive or negative. Because more time, I'll give more detail on that on the video. But if it doesn't say plus or minus, like the direction from the left or from the right, then it's talking about from both directions. So this is from both directions, okay? So real quickly, let me explain those rules because we've got 3 minutes. And I'll explain them better there. So this function is always continuous. It's always continuous. But let's talk about this point right here. This little spot right here. For the first one, it's defined there. It exists there. I just erased it so I could have something to point at. Let me put another color there, right? So it exists there. This function exists there. And the second one, the limit, as we're getting closer and closer to this point, and as we're getting closer and closer to that point, it has a limit. It's that whatever that number is. It's depending on what we put in for x. It has a number. It exists. It exists there, and it is pointing to the same thing. Also, the limit and the function value are the same. So it's heading towards the same thing, and it gets there, right? So it's heading towards the same thing, and it gets there. Here, on this one, there's a discontinuity because at 0, because it doesn't exist, so that doesn't work. And as we're approaching from the left, it gets to negative infinity. As we're approaching from the right, it gets negative infinity. So it's not the same thing. It doesn't exist. It breaks all the rules. I think it's time to leave. Well, I will give more details and more things in the video, and we will have other times to have other questions too. It'll make sense. It'll make better sense when in the video, because I'll have time to do it then, when there's examples. And like in this kind of problem, this is the thing. So that'll help, because you'll see different types of discontinuity and all the things. So, goodbye, children. I'll see you Thursday.